Talk about the resistance, how to calculate the resistance of a resistor. Okay, so in the previous chapter, when we try to calculate the capacitance for different structure of capacitor, okay, there are several formulas, like the one for the parallel plate, like C equals epsilon naught times A over D, and then the other one for the cylindrical, something I don't quite remember, but something like 4 pi epsilon naught L over lateral law of B over A, something like that. And then there's also another one for the spherical capacitor. Here we only have a single formula, okay, and then we don't try to derive it in any sense. So I just mentioned the result here. So the resistance R of a conducting wire of length L and the cross section area A is the cross section area. So the resistance is rho times L over A. Rho times L over A. So probably you may have seen it in high school physics. So actually it implies if you want to have a large resistance, it in some sense related to the material itself. As I mentioned, the rho only related to the material but not the geometric shape. So the geometric shape is here, okay? So resistance is not only related to the material but also the geometric shape. So the L is the length, okay? If you want to have a larger resistance, you increase the length of the resistor. Or you reduce the cross-section area. You reduce A so that you also get a larger capital R. Okay, so which means that if you want to have a large resistor, the resistor should be like long and thin. Okay, long and thin will have a large resistance. If you have a short and fat, okay, short and fat or short and thick, then you will have a small resistance. Okay, so here the resistivity, it actually tells you that it is related to the temperature. Okay, the resistivity is related to the temperature. Okay, so here is the absolute temperature, not the temperature in degrees Celsius. Okay, it's the absolute temperature in Kelvin. Okay, so here it tried to model this resistivity as a linear function. Okay, so this is a linear function. You can see this is the variable t. This is a variable t, and this is a T0. Okay, T0 is a reference temperature. T0 is a reference temperature, and rho zero is the resistivity at that reference temperature. Yeah, because you can see here, okay, this line is not actually a straight line. It's not actually a straight line. So if you model this as a straight line, okay, it depends on which point you are using. Okay, let's say if you are using this point, okay, the line will be something like this, okay, or maybe a tangent line. Okay, I don't draw it very well, but maybe something like this. Okay, so near this point will be more accurate, and then far away from it will be more inaccurate. Okay, but if you want to have a more accurate result, let's say around 1000 Kelvin, okay, so maybe you can take the T0 at this point. Okay, so you will get a more accurate result at high temperature, but not so accurate at low temperature, something like that. Okay, the idea is like this too. So okay, so that's why we have a T0 and rho 0 here. But otherwise, you can just regard it as something like a rho equals something like mt plus b. Okay, just like in high school analytic geometry, like y equals mx plus b. Okay, as a linear function. Okay, so it is something like a slope and then a y-intercept. Okay, it's already a linear function, but Make it like this, just to let you know that, okay, you try to reference to the point T0, okay, the temperature T0, and then with resistivity rho 0, so that if rho equals rho 0, then this is 0, okay, and then T minus T0 is also 0, okay, so 0 equals 0 is correct, and then this is the slope, okay, this is the slope, something like this. Okay. Okay, so here we have we have a table showing some of the resistivity for some material at room temperature around 20 degrees Celsius or 300 almost 300 degree 300 Kelvin. Okay, no degree. Okay, so here we can see usually we will use copper for the wire. We usually will use copper as the wire. So the resistivity is 1.6 times 10 to -8. Okay. Of course, if you want to use some metal to be wire, we would like to hope the resistance to be as small as possible. Otherwise, the wire itself will consume power. This is what you don't want. Yeah, because what you want is you transfer all the power from the power factory to the device you would like to consume power. Okay, you don't want to waste power in between. So the wire, the resistance is smaller the better. Okay, so and in some sense, if it is in a laboratory, okay, so probably they will use silver for the wire. Okay, the resistivity a little bit smaller. Okay, so with we will have a smaller resistance with the same length and cross section area. Okay, but the idea is that the silver is more difficult to rotten than the copper. So for the experimental device, okay, it will be more favored to use the silver as the wire material. Okay, and also the gold. Okay, the gold is very expensive. Okay, and then also the resistivity somehow larger. Okay, it's rather large compared to the copper and silver. The idea to use it just because the gold is very stable. It is very extremely hard to rotten. Okay, 很难生锈，所以就会有些会用哦。所以有一些实验室的话，就是他们的那些什么 PCB， 但是那些印刷板的话，就是会用金来做一些导线的。所以有听过一些新闻是去实验室去偷那些电路板，然后去提炼那些金出来的新闻有看过。Okay, and then maybe we just skip someone. Okay, so these are typical metals. And actually we also have typical insulator. Maybe you are more familiar with. Okay, so actually for the insulator, let's say glass, it has a much larger resistivity, much larger resistivity, or maybe a quartz 就是石英嘛，石英。Okay, so 10 to 16 power. Okay, all of these are 10 to -8. Okay, it is 24 order difference. Okay, so so the insulator have a much larger resistivity. Okay, so for the typical semiconductor, okay, maybe you are not so familiar with. Okay, so here we have several stuff. Okay, so all of them are silicon. Okay, but there are something different. Okay, the first one is pure silicon， 就是纯的硅或者纯的锡啊，看你哪里的翻译，就 pure silicon. Okay, so the resistivity is 2.5 times 10 to the third power. It is quite large. Okay, this is -8. This is 3. Okay, 11 order difference. Okay, but here we have two. Okay, here we have an N-type and P-type semiconductor. Okay, P-type N-type silicon and P-type silicon. Okay, so the the resistivity is much smaller. It's much smaller, 10 to negative 4, 10 to negative 3. So only 5 order difference. Okay, 5 order difference. Okay, here we have a 7 order difference. Okay, so you can feel that yeah, so the idea is that, okay, if we have pure silicon, okay, it is not easy to use. Okay, 就是它的导电性能很差。Okay, so it is like the carbon. Okay, if you're familiar with chemistry, I suppose you have memorized the periodic table. Okay, so for the fourth column, okay, we have carbon and silicon on the same column. Okay, so probably in high school chemistry you have already learned that for the carbon it is not so conductive. Okay, but for a specific structure it is conductive 就是那个碳跟石墨它们都是碳嘛，但是石墨的话它可以导电，类似是这个意思，就是纯的锡、纯的硅它就导电性能很差的，没有什么自由电子，因为它外层4个电子。Okay, but actually for our electronic device, we generally try to use the semiconductor. So we are trying to use it in this way. Okay, one is N-type, one is P-type. Okay, so it can construct something like the MOS, not Mossberger. Okay, this is a metal oxide semiconductor field effect transistor. Okay, the long short form is MOSFET. Okay, and then the short form is MOS, okay, metal oxide semiconductor field effect transistor, 就是中文叫做长效电晶体。OK， 电晶体，简单来说叫做电晶体。OK， 就是一些半导体的元件。OK, so short form we can call it a MOS, and then if it is N-type, okay, we will call it NMOS. Or if it is P-type, we can call it PMOS. Okay, if you're familiar with assembling the computer, you may have seen something called CMOS. Okay, CMOS means complementary metal oxide semiconductor. Okay, so it consists of both NMOS and PMOS to construct the digital logic 就是用来做这个数字逻辑电路或者数位逻辑电路的一些元件就比如说一个 NOT 就可能你怎么说，就是可能你学过一些逻辑，什么 NOT 什么 AND OR 那些就比如说 NOT 它可以用一个这么样的元件去表示一个 NOT AND OR， 或者也是可以类似用一些，比如 AND 可以用6个6个这个东西这个是一个 PMOS。这个是一个 PMOS 不过你不需要知道它是什么，我只是告诉你一下而已。就是这个就是一个 NOT 这个是一个 NOT， 就可以用2个 MOS 一个 NMOS 一个 PMOS 去拼成一个我们叫做 CMOS 的 Digital Logic Circuit 去做这些计算那你说为什么它的导电性能比金属差那么多，我们还是用它因为金属的话它的导电性能是固定的，但是半导体的话我们是可以用电压去控制它的物理特性，它是蛮非线性的，所以反而它会比较有用反而比较有用，因为它很固定的话它就是俗称的铁板一块，它就没有可调性那反而就是这种这种所谓的那个，因为他们这个固定的话，这就是 V 等于 IR， 那就决定了一切那我只能够 我什么都不能做，因为反正你做出来之后，这个 R 已经固定了。那 V 跟 V 跟 I 成一个简单的整数比，那或者是简单的比例的话，那我也不能做什么事情。但是半导体的话，当然这个里面长怎么样的话，那就是电子的课程的内容可以讲一个学期的，就不在这里说，只是告诉你科普你一下，因为我们实验室在做这些东西，对，就是因为它是非线性的元件，所以我们可以用一些电压去控制它的电阻值，可以改变它的电阻值，就它的 I 跟 V 的曲线，它的 I 跟 V 的曲线，它会像这样的，它会像这样的 ，OK， 它就很非线性的一个元件 ，OK， so yeah, so here we have a sample problem. Okay, so it says a rectangular block of iron has dimension 1.2 times 1.2 times 15 centimeter cube. Potential difference is to be applied to the block between parallel sides and in such a way that those sides are equipotential surface. Okay, what is the resistance of the block if two parallel sides are the square end with dimension 1.2 times 1.2 and two rectangular sides? Okay, so for the same structure, we try to use it in a different way. Okay, actually, this one 1.2 times 1.2 times 15, it will be like we have a small square here and then we have a long side here. Okay, so this is 1.2 centimeter, this is 15 centimeter. Okay, so we will try to use it for the first case. The two square ends. Okay, which means for the first case, we try to use it like this. Okay, use it like this. Okay, so we try to see what is the resistance. Okay, when we look into it. Okay, so in this sense, the cross-section area will be 0.012 square, okay, which is 1.44 times 10 to the negative 4th meter square. Okay, so this is the cross-section area. The cross-section area is, let's say here. Okay, this is A. Okay, and then this will be L. Okay, so R equals rho times L over A. Okay, which is this one, 9.86 times 10 to negative 8th, and then times 0.15. Okay, this is the length for this case, and then the cross-section area is 1.44 times 10 to negative 4. So the resistance is 100 micro ohm. 100 micro ohm. 100 micro ohm. Okay, for the second case, okay, you try to use it in a different way. The two rectangular side with dimension 1.2 times 15 centimeter square. Okay, so which means this time it is something like this. Okay, we try to use it like this. Okay, so in that case, the cross-section area for this case will be 0.012 times 0.15. Okay, so which is 1.8 times 10 to negative third power meter square. Okay, so R will be rho times L over A. So rho is the same, 9.86 times 10 to negative 8. So the length here is 0.012 over, sorry, this is not equals, this is multiply, 0.012 and then over 1.8 times 10 to negative third power. Okay, so this is 0.65 micro ohm, like this. Okay, so you can see that Okay, so this is much shorter and much thicker. Okay, this is long and thin. So you will also expect this resistance is much larger than this one. Okay, this. Okay, so this one is quite easy. Just try to plug in all the values into the formula for calculating the resistance of a rectangular structure. Okay. Okay, so here we have a slide called Ohm's law. So there are quite a lot of words, but we don't need to see that. Okay, so what we need to know for the Ohm's law is V equals IR. We just forgot everything else. Okay, so it is as simple as, okay, here we have V, we have I here. Okay, V I, or maybe you can just exchange. Then what you can plot is a straight line. Okay, the relationship between the current and the potential difference will be a straight line, and then this loop will be 1 over R. This loop will be 1 over R. If we exchange V and I, okay, if we draw it like this, V and I, and then this, in this case the slope will be R. So it depends which one is the x-axis, which one is the y-axis. And just as what I mentioned last time, okay, every time when we define, okay, if we have a V, okay, this side is higher, this side is positive, this side is negative, which means V will be the potential at this point subtract by this point. Okay, let's say if we call this point is VA, this point is VB. Okay, so V will be VA minus VB, the positive terminal subtract by the negative terminal, the potential. Okay, so in that case, the current direction will be from the positive side to the negative side. Okay, like this. Okay, this is the direction of I. Okay, so you need to remember it very, very well. Otherwise, you will have a mistake for the sign. Okay, so for the metal or for the conductor, okay, this kind of material will satisfy this Ohm's law, but there are some other conducting device which is not so linear. Okay, so here is just an example. Okay, so here it shows this is the potential difference and this is the current. Okay, but this is not a straight line. It will be like 0 all the way up to here, yeah, and then go up very fast. Okay, it is actually an exponentially increase. Okay, do you know what is this device? 有没有人知道这个是什么元件？ OK， 这个叫做二极体啊，这个叫做二极体。这个是一个 diode， 啊，也是一个半导体的元件啊，中文叫做二极体。好，如果学一些那种电子的课的话，它其实我们也会把它叫做一个 PN junction 啊。PN junction 中文叫做 PN 的界面啊 ，PN 的界面这是一个 P 型的不会画立体图一个 P 型的跟一个 N 型的一个半导体啊。哦，刚才忘记说了，那 P 型跟 N 型是什么意思啊 ？P 型半导体的话，就是说我们先提纯一些很纯的硅啊，很纯的硅。那 它原来就是那个导电性能很差的，所以那个 resistivity 很大的。那我们 N 型的话，我们就掺杂一些五A 轴的5A 族的一些元素啊，掺杂完五A 族的元素之后，它就会在外层有一个自由电子，所以它就是我们叫做 N 型就倾向于带负电荷的那种感觉。那 P 型的话很简单，很好理解加5A 族的话，它就变成 N 型的话，那我加3A 族的某些元素的话，掺杂这些杂质进去就是很奇怪，就是我要先把它提纯，然后我加一些杂质，掺杂一些杂质进去之后，它的导电性能就会变好它导电性能变好 ，N 型的是因为我掺杂完5A 族元素之后，它最外层就有9颗电子，就多出一个出来，那个就会自由自由的去导电。当然，它只有一颗是自由电子，跟导体不一样的话是外层的都是外层比较多的自由电子，所以金属的话导电性能比较高那半导体的话就差一些但是我们可以比较有可能去控制它那 P 型的话，我掺杂完3A 组之后，那最外层就有7颗电子，就缺一颗。缺一颗的话，我们就把那个叫做电动叫做一个 hole P 型的话，我们就会有一个 hole电动的存在。电动电动，它就是缺了一个电子，所以的话就是其他的电子看到这里缺了一个，就会有可能去补位，所以透过这种方式就是比较间接的，它有一个相反的自由电子的一个感觉，但是它还是有空位给电子去移动所以 P 型的话，它的导电性能是差一些的P 型的话，这个是比较大嘛，所以它的导电性能是差一些的，通常会差到2到4倍左右所以这个二极体的话，也是一个半导体的元件好，那这里我跳过吧。Okay, so here we have another slides about the Ohm's law, but from a microscopic view 从一个微观的形式为什么我们要做这个动作呢？就是说本来的欧姆定律它是怎么来的？本来的欧姆定律就是说，那些物理学家就是没事做嘛，所以他就尝试去测量很多的这种改变应该是说就没事做嘛，就是拿着一个电阻那我就改变它的电压，然后去测它的电流，然后一直改就看到这样。那然后的话就是说，那这个的话就相当于是一个我们叫做回归的动作，就是 regression 的动作regression， 透过 regression 的方式，就是差不多是一个回归啦，线性回归的那种感觉线性回归在这个情况是一个 linear regression 线性回归俗话说就是 feed 一条直线给它。那这种的话，就是说它的理论基础没有很强，因为我们只是透过一个测量可能它就点很多点它看起来像一条直线，我们就弄一条直线，但是它只是看起来像，它也许就不像那所以它没有太多理论基础，它只是单纯透过实验的结果，我们得出这个结论的话它是一种方式。我们也不是说它不可靠，但是如果我们有另外一种方式，从另外一条路也能告诉我们说它应该有这么一个常数，会让它像一根直线的话，那 我们相信它的信心就会大一些，所以我们需要有这个 microscopic view. Okay, so here it says the assumption that the conduction electron in a material are free to move, like the molecules 就是这个分子 in a gas leads to an expression for resistivity of a material of a metal. Okay, so here we try to assume there are some particle. I mean the free electrons. Okay, so for the free electron, it will be like it try to move, and then for simplicity, okay, we try to assume it start from rest and then it try to accelerate, and then maybe it will collide something else at a certain moment, and then it will reflect. Okay, so it will try to go from here to here, and then collide something, and then reflect, and then collide something again, and then reflect, something like this to repeat this process. So it will go for a strange locus. Okay, so here it says if an electron of mass is placed in an electric field of magnitude E, the electron will experience an acceleration. OK， 他就说，如果它在一个电场里面，一个电子在一个电场里面，它就会有这个库仑力嘛，就是有这个 F equals QE 嘛。OK， so as much as we have a force acting on this electron, according to Newton's second law of motion, there will be an acceleration. So this A equals F over m, and F equals QE. Okay, so for this case is E. Okay, we just ignore the negative sign, or we just consider the magnitude. Okay, so F equals E times small e times capital E. Small e is the elementary charge, and capital E is the E field. Okay, so here we also assume that the drift speed is Vd to be A, this acceleration times tau. Tau will be the average time between collision. OK， 就是平均它会碰撞的那个平均它会碰撞的时间，就是有可能它从 A 到这里就经过比较长的时间才碰撞但是碰第二次的话就快一点这个又长一点的，又短一点，就是平均的会碰撞的时间。我们就假设它每一次都是从静止加速碰撞然后又从静止又开始加速又碰撞一直循环这个碰撞的动作。所以算出它的这个 drift speed 是这个 Vd 等于 A 乘以 tau tau 这个是一个 Greek letter 就是 T 的那个 Greek letter 是 tau. Okay, so here we try to plug in A, okay, A to be here, okay, which means we try to plug in this stuff to here. So we have E times capital E over M times tau to be this V. And also, previously we already have a J equals NE times VD. And then we try to plug in this VD with this expression to here. So we have NE and then times E times capital E and then M and then tau here, something like this. Okay, so here we try to get the expression of E, okay, in terms of other terms. So we remain E here and then we try to move all the other stuff to the left hand side. So J is here and then M go to the top, E square go to the bottom, N go to the bottom, and then tau also go to the bottom. So here we have this E equals M over E square N tau times J, okay? And then previously we already have an equation called the vector form of the Ohm's law, E equals rho J. Okay, so comparing these two, okay, we can see that this rho should be M over E square N tau, okay, something like this. And okay, so here m is the mass of an electron, which is a fixed value, which is a constant, 9.11 times 10 to negative 31 kilogram. And then E is elementary charge, 1.6 times 10 to negative 19. And then this is N. N, what is N? N is the charge density. N is the charge density. So it will be a fixed value for a specific material. Okay, and then tau. We also assume that this is fixed for a certain material. Okay, because for the collision, it will be something like it is a metal. Okay, so it will have a structure something like, okay, we have many atom of a metal, atom of a certain material. So the electron may go through. Okay, and then for some time it may collide with a certain atom and then try to refract. So for different material, this kind of structure is fixed. Okay, the distance between adjacent atom or the shape should be, or the topology should be fixed for a material. So for fixed material, we'll assume that this kind of average time between collision is only related to the material itself. So in that case, okay, this is a constant or only related to the material. Okay, so for different material, this constant may be different. Okay, so it also explains that, okay, this is the resistivity only related to the material. So due to this simple derivation, we know that, okay, we should have a rho which is only related to material. Okay, to making this thing reasonable. Okay, so to making this thing reasonable, this is so-called the vector form of the Ohm's law. Okay, so yeah, so if this is correct, we also assume that V equals IR is also correct due to this derivation. Okay. Okay, so maybe I can also verify that this is actually the vector form of the Ohm's law. So this one and the V equals IR is compatible. So we can actually we assume that the E field is constant. So we have E equals V over L. Okay, E equals V over L. So we assume the E field is constant. So the potential difference is V over the distance. And then also J, we also assume it to be a constant. So J equals I over A. Okay, J equals I over A. So in that case, rho equals E over J. Okay, so the idea is that we try to assume this is correct. And then by some sense, we try to derive it is compatible to V equals IR. Okay, so here we try to substitute E equals V over L. So V over L here, and then J is I over A. So A over I here. Okay, so in that sense, we can combine V over I here and A over L there. Okay, so it turns out that V over I is actually R. And then times A over L. Okay, so when you look at the very left side and the very right side, okay, so we can slightly rearrange. We can actually get R equals rho times L over A. Or maybe if you use this one, you can somehow derive it becomes V equals IR. Or if you use V equals IR here, then you can actually get this one. Okay, so you can see somehow verify that all these formulas have some sort of relationship. Okay. Yeah, so so here we have the rho equals this one just as what we derived in the previous slide, and then here it says n is the number of free electron per unit volume. Okay, so which will be the particle density, and then tau is the mean time between the collisions. Okay, so metal obey Ohm's law because the mean free time tau is approximately independent of the magnitude E of any electric field applied to a material to a metal. So it only relates to the material itself. Okay, so here we have a simple sample problem. So for the first question, it asks, what is the mean free time tau between collision for the conduction electron in copper? Okay, so here we just need to use tau equals m over n e square rho. Okay, for the mass is 9.11 times 10 to negative 31, and then n is this one, 8.49 times 10 to 28 power. And then E is 1.6 times 10 to minus 19 quantity squared. And then rho is this one, 1.69 times 10 to negative 8. Okay, so this is actually 2.5 times 10 to negative 14 second. Or if you try to write it in with a scientific prefix, so it will be 25 femtosecond, which is really short time. Really short time. Okay, so this is easy. So we just plug in the number into the previous formula. Okay, so for question B, okay, it asks the mean free path tau, lambda. This is lambda of the conduction electron in a conductor is the average distance traveled by electron between collisions. What is lambda for the conduction electron in copper, assuming that their effective speed E effective is 1.6 times 10 to the 6 meter per second. Okay, we make this assumption. Okay, so here we have a lambda equals VEFF times tau. Okay, so it's just what you learn in primary school. Okay, the length is the speed times the time. Okay, so it is actually 1.6 times 10 to the 6th power, and then times 25 times 10 to negative 15. So this is 14 nanometer. 14 nanometer. OK， 所以这一题就很简单，其实就是带一些很简单的式子。但是其实怎么说，就是有些时候这本书出一些例题，有些时候是告诉你说，哦，这个计算很复杂，怎么样操作，告诉你。有些时候他用一些例题来说一些物理的故事啊，这一题就是其中一个用来说故事的。OK， 所以这里就说 ，This is about 150 times 150 times the distance between the nearest neighbor atom in Cooper lattice Cooper lattice 就是在一个铜的晶格里面，它就有一个固定的间距嘛，所以说他就说这个40纳米的话，相当于150倍的相邻的那个距离啊，所以它的意思就是说，它会穿过150个原子核啊，它才会碰到。所以 thus it says on average each conduction electron pass many Cooper atoms, around 150 atoms, before finally hitting one. 所以这个计算出来的结果这个40纳米或者是30几、50几，它不一定需要很准，但是大概这个数字它会经过100多个铜的原子，就代表说它它等于说是佐证，原子应该有一个原子核，然后外面有相当大的空间在，而不是说它很紧密的。如果它很紧密的排在一起的话，那电子不应该可以穿过那么多才碰到一次因为它不会人会躲，不会走路不会撞到别人它就会尝试去电子的话，它没有办法控制自己往哪里走嘛，它外面的力作用在它身上，它就往哪里走嘛，所以它还能够穿过那么多的话，代表说一个原子的结构应该是一个很密集的一个原子核，让外面有很多空间，电子能够通过。所以在佐证这个事情，因为在那个时候的话，应该他们还不知道还不确定有这样的原子结构Okay, so here we talk about the power. Okay, so the power will be like P equals IV. Okay, this is always true. This is always true for all the device. Okay, as much as you try to multiply the current and then the voltage across it. Okay, this one is off. So maybe like this. Okay, so I times V will be the power consumed by this device. This is always true. Okay, no matter whether it is a resistor, capacitor, inductor, or whatever nonlinear unit, or maybe the moles. Okay, this equation is still correct. But for these two, it only apply for resistor. Okay, you cannot apply this for other device. Okay, so the idea is like here, with this one, you try to plug in V equals I out. So this one should be this one should be I square out. This one should be I square out. So this equation, as you can see, with an out there, so it can only be applied for the resistor. And similarly, if you try to plug in I equals V over R, then you will get V squared over R for the power consumption of a resistor. Okay, so this one is just from a very fundamental point of view to let you know why P equals IV. So the energy will be the small energy U du will be dqv, and then okay, so dq will be I times dt. Okay, so this is the definition for the current. Okay, so here we have IV dt, and then we move this dt to the left side. So P is du dt. Okay, so power is the energy consumption per unit time. Okay, so which become IV. Okay, so it tells you that, okay, so the only thing we use is this one. Okay, U equals QV is a very beginning definition, and also Q equals I equals dq dt. Okay, so only based on these two very fundamental definition. So it tells you that P will be IV, only satisfying that two assumptions. Okay, so finally we slightly talk about the semiconductors, just as what I mentioned. Okay, so I don't try to repeat again. So yeah, so roughly speaking, in the middle of the periodic table, we have some semiconductor. So the mostly used material will be the silicon, and actually some other material like germanium or some other material, we will still like to use it for some other application, but silicon is the most cheapest material to use. I say. Okay, so actually, so the MOS or CMOS are widely used for digital circuit and also some other analog circuit. We'll still use the silicon. And another one is called a superconductor. Okay, this one is called 超导体。Okay， 这个就比较困难一些比较困难一些。就是我也没有这么学过它，因为这些是一些很材料的事情，材料的事情。因为刚才我们就说嘛，就是前面的话有一个地方是什么 rho 减 rho 0等于什么 rho 0，然后我忘记了 kappa 还是什么乘以那个 t 减 t 0之类的类似像这样一个式子 ，OK。那个时候那个线呢是这样接近直的，有一点点弯的那种状态那如果你这样就满足的话，那就结束了。但是那个时候的人就是闲来无事他们拿到什么？他们拿到一些 liquid helium， 就是拿到液态氦拿到液态氦。液态氦的话就可以降到这个接近绝对0度可能绝对几度的地方。如果再用一些什么加压的一些技巧的话，就可以什么 PV 等于 nRT 那种东西，改变一下那个气压的话，就可以改变那个绝对温度可以到什么绝对1度以下的。所以他们就闲来无事就是降到那个绝对4度左右就发现这个 mercury 就是这个水银就是那个汞就突然间这个 resistance 突然间就降到0了，突然间就降到0就降到0呢，就是 perfect 一个0，这不是一个很小的数，是绝对的0那这个 so this phenomenon we call it the semiconductor effect. Okay, so actually for the superconductor we need very low temperature. Okay, so of course at the very beginning we need it as low as close to 0 Kelvin. Very close to 0 Kelvin. Of course you cannot really achieve 0 Kelvin or even lower than 0 Kelvin. You can never do that. But you can approach 0 Kelvin, like 100 of millikelvin, okay, something like that. Yeah, but of course for the physician guy or the material guy, they will try to find some material so that to increase this temperature, that maybe a certain material can have this kind of superconductor effect. 就是这些做材料的人，他们会尝试找一些材料，他们是有这种超导性质的，然后也不需要到绝对0度或绝对4度这么低的温度他们在做的事情。但前1-2年的话，好像有一个新闻说找到一个常温的超导体，然后后面被人说它是造假的 ，OK， 就是传出来那几天就是所有人都在重复它实验，就全部人做不出来，然后就说它是造假的 ，OK。Okay, so maybe we have a 10 minutes break first.